Okay, so last chapter we did what's called a z-test, and with that z-test we are saying we have a sample mean, and we think that that sample mean maybe is different than the population mean. In this example, with the z-test, you have your sample, and you have the population mean, and you have the population standard deviation. If you did not have the population standard deviation, and you had like a guess as to what you thought the population mean was, you can run what's called a one-sample t-test. So z-test, you do that if you have the population mean and standard deviation. You do the one-sample t-test if you don't have those, but you have like a guess as to what the mean will be for the population. So yes, in the last chapter when we had this, we had those test scores, and our sample mean was 533, the population mean was 500, the standard deviation was 110, the sample size is 100, so we had a lot of information. We took the 533 minus the 500 divided by 110, which is divided by the square root of n, and we got, I don't remember what it was, 2 or 3, a critical, or the z-score was like 2 or 3. And if I recall correctly, our our sample was significantly different from what we perceived to be the population. Same thing with the females' pay compared to the national average. We did this last chapter. But yeah, so in theory, if we had just that sample of 100 women and we had their salary, but if we didn't have population mean and the population standard deviation, then we'd have to do something else. We would do this one sample t-test. It's pretty similar. So we're going to take our mean minus what we think could be the population mean. We'll talk a little bit more about that in a second, divided by the estimated standard error of the mean. And that's this symbol here, which is the standard deviation. In this case, it's going to be the standard deviation of our sample divided by the square root of n. And you can take both of these formulas and put them together, and it looks like this. Imagine it looks prettier than this, but our mean minus population mean divided by the standard deviation, which is divided by the square root of n. So it's not that complex of a. It's wordy, but it's not really that terrible of a calculation. Just some refreshers. Standard deviation is like a rough guess, a measure of how far the data is spread out, how far scores are deviating from the mean. This would be within your sample. The standard error of the mean, this is how far our sample mean is away from what we perceive to be the population mean. How far the sample mean is likely to be spread from the true population mean. A couple of other ways of saying it. The standard error of the mean indicates how different the population is from the sample mean. And yeah, you take, to get that SEM, standard error of the mean, you divide the standard deviation by the square root of the sample size. And yeah, obviously the SEM is always going to be smaller than the standard deviation because it's being divided by your number, your n. All right, so here is an example. Let's say we think that the average age at a daycare should be 2 years of age. You can see where my mind's at when I'm creating these samples. I was thinking about daycares, and I was thinking about kids' age. So yeah, let's say it's going to be 2. That's our guess. So it's just a guess, so we don't actually have the mean, and we don't have the population standard deviation. We're guessing 2, but we want to do this as a two-tail because, that idea that we want to catch it at either ends. What if our mean turns out to be 3? Or what if it turns out to be 1? If it's a two-tail, we can catch both a 3 and a 1, if that's the significant difference. If we just set it at one tail, it's going to be less than 2, or it's going to be greater than 2. We don't really have a theory for that to suggest that. So we collect the data. We got 3 kids in the daycare, and their ages are 1, 3, and 5. In this example, the null hypothesis would be that our sample essentially equals 2, because that's what our guess is for the population mean. The alternative hypothesis is that it does not equal 2. So pretty straightforward. So we just calculate our mean and the standard deviation. Here's the standard deviation for a sample. You got to take each score away from the mean, or minus the mean. You got to square it. You got to take them all together and then divide them by the degrees of freedom, n minus 1. So we got our 1, 3, and 5. If you add those up, that's a 9. Divided by 3, it's 3. So we would take minus 3 from each one. And we're going to get a -2, a 0, and a 2. And you'll recall that if we added those up, they would equal 0, always equal 0. You also recall with degrees of freedom, We know that this one has to be a 2 because we have a negative 2 here, and this is a 0. So this one has to equal 2, so that means that this one number had to have been 5. So that number is not free to vary. That's the term for degrees of freedom. So anyways, because of that, we have to square each number. So we square it, get a 4, we get a 0, we get a 4, we add them up, 8. We're going to divide by n minus 1, we had 3, so 3 minus 1 is 2. We get a 4, square root of 4, we get 2. So 2 is our standard deviation for this sample. Which intuitively, you kind of know this. If you think about the mean here is 3, and this one's 2 off, and this one's 2 off, and yeah, the standard deviation is going to be 2. And so we plug this into our t-test, our one sample t-test. And 3 minus 1 divided by our standard deviation, the 2, divided by square root of n. We'll get a 1 divided by 1.15, which is going to equal 0.87. You're like, great. Okay, so we got a t of 0.87. What do? Just think about it for a second. What have we been doing? It seems like constantly here recently. We'll go back and check some table. So here's our new table, critical values of t. This one's a little bit easier to read, I think, in my mind anyways. So this one's two-tail, meaning that we're looking at both ends. So it could be, 3 or 1. If you did a one-tailed, your t-crit would just all be on this side, not the other side. And you could flip that if you wanted to. Or just have everything on this side, nothing on this side. We have our degrees of freedom. We have p at 0.05, at 0.01, and 0.001. And so our degrees of freedom was going to be 2, because it was in 3 minus 1, so 2. If we were looking at, and let's say we probably would just start at 0.05, we would need to get a t-value of 4.3 for it to be significant. Technically, a 4.304 would be significant at the 0.05 level. And we don't have that. We have a 0.87, so it's not even close to being significant. So yeah, degrees of freedom, n minus 1, degrees of freedom is 2, and then that's what we would need for that t-crit value, which we didn't even get close to. That's how you do it by hand. You're never going to do it by hand, but just I thought I'd just show it to you. In SPSS, we're going to click Analyze, Compare Means, One Sample T-Test. Let me reset this. We'll move age over. Here's the part where people are going to make mistakes. This test value, you have to put the number in there that you think the population mean is. And we had guessed it was going to be a 2, so put a 2 in there. Click OK, and we'll get our output. Looks pretty familiar. N of 3, mean 3. There's your standard deviation of 2. Our standard error of the mean was that 1.15. Our t-value is 0.86, degrees of freedom 2. So a one-sided p and a two-sided p. Again, we were running a two-tailed, so a 0.48, 0.478. So definitely not even close to less than 0.05. We'll talk about a couple of these other things in the next example. Let's get to it. Let's see. Accept the null, retain the null, keep the null, however you want to say it. It's not significant. There was an example in the book. I think it was for gas mileage. They were saying that cars' gas mileage, they were guessing it should be about 45. And so we got a sample to see if our cars were getting 45. The book kind of did something weird. It started off as a one-tail and then it switched to a two-tail. I don't remember the exact thing, but this is written up as a one-tail, essentially. That our gas mileage is either going to be equal to or greater than 45, or the alternative hypothesis is it's going to be less than 45. So if you just think about that, if you're just doing it less than 45, that would have to be a one-tail, because everything would have to be less than 45. When we actually go through this example, though, we're doing it as a two-tail. So what this would actually be is, if we're doing it as a two-tail, instead of being less than 45, it would just be not equal to 45. The first one, the null would be equal to 45. The alternative would be not equal to 45. All right, so we'll go to SPSS, Analyze, Compare Means, One Sample T-Test, Compare Means, One Sample T-Test, reset this, move gas over. We'll put our test value again at 45, click OK. N of 6, our mean is 43. Standard deviation is 2.2-ish. Standard error of the mean is about a 0.9. We're going to get a t of negative 2.236. We could go to that table and look that up with the degrees of freedom of 5. It's an interesting situation here. So if we had said it was a one-sided p that was going to be less than 45, If we'd said that before we started the analysis, it was going to be less than 45, we would have gotten a p less than 0.05. We didn't in our example, and so we get a two-sided p at value of p is greater than 0.05. It's super close, but it's greater than. Again, a cheater would say it was just a one tail and redo it, the entire thing, but again, that's not the way you should do it. If you did have a theory that it would be less than 45, great, but if you don't have a theory, you have to pick it one tail or two tail before you run the analysis if you want to be legitimate with it. The mean difference is 2. Yes, so we set a 45 and our mean turned out to be 43, so there's a mean difference of 2. On the confidence intervals, let me go back to the PowerPoint here and see what we have. Confidence intervals are a range of values that we're saying within a degree of certainty an unknown population characteristic, in this case, the mean. So we have a range of values and we're pretty sure the actual population mean is somewhere between these two numbers. How we get that is we're going to take our sample mean and we're going to take it times the t critical value times the standard error of the mean. So this is what that would look like. We could go back to the t-crit table to get that 2.57. I can just show you real quick. 2.57. What did we have? Degree of freedom 5 for 0.05, 2.571. That's where it's at. And so our standard error of the mean, which was calculated by SPSS, was 0.89. Take those times each other, and then you would have your sample mean, the 43, plus or minus what that is to get that range. And so we have a 45.29 to a 40.71. So we're pretty sure that the population mean, the true population mean, if we were to get every single data point for that, we're pretty sure the mean would be somewhere in here. When we're saying a 95% confidence interval, we are 95% sure that that population mean is somewhere between 40.71 and 45.29, which, yeah, makes sense. So our 43 is going to be somewhere in here. Our original thought was a 45, and so 45 is almost outside of that range. And once you get outside of that range, or if you're not almost overlapping anymore, it's probably going to be a significant difference, like it was getting really close. So in that two tail, we had the 45 here. If we had it all one tail, then it probably would have been in there, and that's why it was significant. It's not precise, but like if your guess doesn't overlap with the confidence interval, it's probably significantly different. Like if 45 was out here, it'd be like, okay, they are significantly different. This is how we write these up in APA style. So we've got our t in the degrees of freedom, our t statistic, and it's p greater than or less than. This is how you'd write it up. Gas mileage in our sample was lower than 45, and you'd write the means 43, the standard deviation is 2.19, but this difference was not significant. You would list your 95% confidence intervals, which was negative 4.29 to 0.30, and then yes, T5, 2.24, P greater than 0.05. On these confidence intervals, if you think about it, so that 45, if you add 0.3 to that, that's what this is here, 45.29, 45 minus 4.29, that is essentially 40.71. So that's where those numbers come from. Yeah, if both of these numbers were negative, that would mean that our guess was not within the confidence interval, so maybe it's going to be significant, or if they're both positive, because that's what you're saying is that your mean's here, but your confidence intervals, both of them, are that direction. And I have one more example where I believe that actually happens. Let's see. Analyze, compare means, one sample t-test. We'll reset this. Move protein. These are protein bars, and we think that we gather up a bunch of protein bars, and we think that the average amount of protein per bar, protein grams, should be 20. And so we'll click OK. N of 31 means 21.4, so maybe it is significantly different. If we come down here, we'll see you've got a T of 3-ish. One-sided P, two-sided P, doesn't matter. They're both less than 0.05. We would have probably put it as a two-sided P because I don't think we had a theory on this, and so it would be P less than 0.01. We have our confidence intervals here, and again, these are both positive, meaning that our confidence, we're pretty sure that the actual amount of protein per bar is either somewhere between 20.5 so I'm getting the 20 test value, 20.46, or that's the lower end. The upper boundary would be 20 plus this here, so 22.33, meaning that that test value of 20 isn't even within the confidence intervals, and that, yes, would suggest that it's probably going to be significant. And then I have another example of how to write this up, and I color-coded it so you could think through this. It's like, okay, you're looking at that SPS output, you're going to need to find the mean and the standard deviation and the confidence intervals and the t and this. So these are going to get more and more complex as we go through these. So this is the one sample t-test, then we'll do two sample t-tests, then we'll do ANOVAs, and we'll have lots of things we'll have to start listing. I had a student last semester that was into color coding things, and so then I started doing it too to try to, help her out, and maybe this will help some of you out too. So we're looking for the mean. We got a 21.4. I got it here. That's the red ones. Our standard deviation, this yellow or orange, whatever that is, 2.54. Our confidence intervals, 0.47 right there, 2.33. Our t, the green one, is 30 degrees of freedom. Our t value, the blue one, 3.07, and p is going to be less than 0.05. I think if I was to rewrite this, I would write it up as p is less than 0.01. All right, that's it for the one sample t-tests. And again, next time we'll get into two independent samples t-tests. We'll run two different groups. This is where we get into like actual experiments where, if you have like a drug study where you run one group takes a medication and one group takes a placebo, and then you were to measure something, and then you compare those two groups to each other. That's an independent samples t-test. And so I think that's where things get really interesting when you start running those true experiments. All right. I hope that if you have any questions, please let me know. Thank you very much for listening.